Hi everyone. In today's video, we're going to talk about a reaction called Diels-Alder reactions. We're going to focus on its mechanism, some energetic considerations, and stereochemical outcomes. It is my goal that by the end of this video, you should be able to explain why we actually consider Diels-Alder reaction a pericyclic reaction, which we'll talk about. You should be able to draw, obviously, the mechanism of this reaction using your curved arrow notation. You should be able to identify the ideal starting materials or the reactants needed to make this reaction really efficient, as well as the reaction conditions that are really good for Diels-Alder. And then we'll end with some case scenarios on how to predict the stereochemical outcomes of Diels-Alder reactions. So to help us lead into Diels-Alder reactions, we first need to describe what a pericyclic reaction is. And there are certain characteristics that, taken together, define a pericyclic reaction. And the first is pericyclic reactions are characteristically known as one elementary step reactions. And what this really means is that throughout the reaction, there are no intermediates that we should expect to be formed in this reaction. And so if you're thinking about a reaction coordinate diagram for a pericyclic reaction where you have your reactants on one end and your products on the other end, you should expect to see only one hill that connects the reactant state to the product state. So there are no intermediates in between these two states. And therefore, the reaction as a whole goes through and finishes up in only one elementary step. Secondly, pericyclic reactions are known to go through a cyclic transition state. And in fact, this is where that name pericyclic is really like coming from. In the transition state, you would see essentially electrons moving around in a cycle or a circle in a closed loop. So here's an example of what a pericyclic reaction transition state would look like. And so in this example, we see that there are two molecules that are actually coming together, and those red dotted lines represent the electrons moving around in a closed loop. And it's that closed loop that really defines the fact that we're going through this cyclic transition state. And we will certainly come back to this particular transition state as we go into the Diels-Alder reaction in this video. And then lastly, in a pericyclic reaction, the product outcomes, so what happens in the product state, is really affected by two conditions. One is called the heat condition or thermal conditions, or under light conditions, otherwise known as photochemical conditions. And we will come back to this last point in a different video where we really talk about the product outcomes under these two thermal and photochemical conditions. So now that we've defined pericyclic reactions, we will now turn to cycloaddition reactions. And cycloaddition reactions are actually a subcategory of pericyclic reactions where two conditions are met. Condition one is that two pi bonds are broken in the reaction, and in condition two sigma bonds are formed. So simultaneously in this one reaction step, cycloaddition, you should expect two pi bonds breaking and two sigma bonds forming. So I'm going to show you an example of a reaction that will be considered a cycloaddition, and I want you to note the number of pi bonds that are breaking and the number of sigma bonds that are forming in this reaction. And so in this reaction, we have two reactants. One of them is a diene. You see the two pi bonds in the diene on the left. And the other is just an alkene, where we see a one pi bond on the right. Which means in total, we have three pi bonds in the reactant side of this reaction and four sigma bonds on this reactant side. When the reaction occurs, this is the product that ends up being formed. And what I wanted to do is take note of the bonds that have been formed and the bonds that have been broken. And you might be able to see that there is now only one pi bond in the product, which is 2 less than what is in the reactant side, and 6 sigma bonds on the product, which is 2 more than what we saw on the reactant side. And so because we're seeing this, it sort of falls under that subcategory of pericyclic reactions where 2 pi bonds are broken and 2 sigma bonds are formed. Okay, so now we're in that definition. So this is an example of a cycloaddition reaction. And once again, I'm teasing you with this reaction because we're actually going to be focusing on this specific reaction in this video. And the reaction I've been teasing you with is called a Diels-Alder reaction, which we have already established is an example of a cycloaddition pericyclic reaction. But there's a specific definition for a Diels-Alder reaction which separates it out from other cycloaddition reactions that are available to us. And so for Diels-Alder reaction specifically, we need 4 atoms of a conjugated diene reacting with 2 atoms of an alkene, also known as a dienophile, in your Diels-Alder. And so because of that requirement, Diels-Alder reactions are known as a special example of a cycloaddition reaction that is specifically called a 4+2 cycloadditions. Once again, that 4 comes from the 4 atoms of the conjugated diene reacting with the 2 atoms of the in a pi bond of another molecule, which we're calling a dienophile. So that 4+2 cycloaddition comes from the combination or the addition between these 2 sets of atoms. And so if you're doing the math, when the reaction occurs, a 6-membered ring should then be formed as a product of this Diels-Alder reaction. Okay, and so now we're going to take a closer look at the mechanism of this Diels-Alder reaction. So like I said, we start where one of our reactants is a diene or a conjugated diene, and see how I'm drawing sort of a fundamental or simplest diene in organic chemistry. And we note here that there are 4 atoms that are involved in that conjugated diene, which I am numbering as 1, 2, 3, and 4. And then as my second reactant, we have our dienophile, which is really technically any molecule that has a pi bond. And so here we see that there are 2 atoms involved in the pi bond. And I'm numbering these 2 atoms as 1' and 2', just to separate from the 1 and 2 numbering of the diene. And so we see here that ultimately we have 4 atoms on one side, 2 atoms on the other side, and the reactants are what we're showing is the conditions for our Diels-Alder, a conjugated diene and a pi bond. And so in our mechanism, the way this reaction goes is you have your electrons essentially moving around in a ring or in a closed loop. So I'm going to show you the electron motion as this Diels-Alder cycloaddition occurs. And so here we can draw a curved arrow where we might start from the dienophile pi bond, where that breaks, and then the electrons are being used to form a bond between carbon 1 and carbon 1'. Then the 1,2 pi bond breaks, and the electrons move over to form another pi bond between carbons 2 and carbons 3. Then the 3,4 pi bond breaks, and the electrons are used to form a sigma bond between carbon 4 and carbon 2'. And if you're following this, you might see that our product will look like this 6-membered ring. And numbering accordingly to our reactant side, we see here that essentially the 1 and 4 position of our diene has bonded with the 1' and 2' position of our dienophile, and then altogether we have a 6-membered ring that has formed. Please once again note that it's a cycloaddition because we reduce the number of pi bonds by 2, and we increase the number of sigma bonds by 2, right? So we've already discussed that earlier on. And note the position of that pi bond in the product side. We can certainly depict this electron motion in our transition state, where we might see that what is really going on here is electrons moving around in a loop, right, which is characteristic of a pericyclic reaction. So this is something we've already established in the beginning of this video. Okay, so this is the mechanism of a Diels-Alder reaction. It is pericyclic in nature. It requires a diene. It requires a dienophile, and then you form a six-membered ring, and then you should make sure that because of cycloaddition, your pi bonds are reducing by 2, and your sigma bonds are increasing by 2. Okay, so now that we've established the overall mechanism and the overall energetics of our Diels-Alder reaction, we're going to now go into a little bit more detail on how our substrates affect the reaction itself. And we will once again use our example, the Diels-Alder reaction, as a guide to help us understand substrate effects. So recall that ultimately we need a diene and a dienophile to form the Diels-Alder product. Okay, and so now we're going to focus our efforts on the dienophile. And so it turns out that the nature of X, so I've been sort of just showing you a generic X on the dienophile, but the nature of X actually matters. Experimentally, we know that Diels-Alder reactions will proceed faster and with higher yields, so you get high yields of your product, if that X is an electron withdrawing group. So here are some examples of groups, X groups. I'm going to first give you an example of bad X groups, which makes it a terrible dienophile. And then I'll give you another set of examples of good X groups, which makes the dienophile really good for Diels-Alder reactions. So here are some examples of bad dienophiles. We see that in the first molecule, X is basically a hydrogen, and in the second molecule, X is a CH3 group. And both of these, none of these are electron withdrawing groups. And so if you try to do a Diels-Alder reaction with these dienophiles, you would have to really heat up your system. And we're talking about hundreds of degrees Celsius. And so this is a really like tough reaction to do if you're trying to use these bad dienophiles. On the other hand, here are some examples of good dienophiles. These dienophiles, you can use them on dienes and do a Diels-Alder reaction under room temperature. And we notice that in the common thread between these three examples is that X group, all of those X groups are electron withdrawing. And so hence we see a pattern here. The more electron withdrawing your dienophile X groups are, the better your dienophile is at engaging with a diene in a Diels-Alder reaction. And now let's focus on the diene, so the other substrates in our Diels-Alder. And the key factor that affects the reactivity of our diene is actually structural. So the structural requirement for a diene to engage in a Diels-Alder reaction is that the diene must exist in what we call an S-cis conformation. And here's an example of a diene that can exist in the two major conformations of dienes. On the left, we have the S-trans. Notice the positions of the two double bonds around the single bond. And then that single bond can rotate, and you can then get the diene into an S-cis conformation. So both of these conformations will exist for this particular diene, but the S-cis conformation is the one that engages in our Diels-Alder. So with that in mind, we can actually start to think about examples of bad dienes, so dienes that can never really do Diels-Alder, and dienes that are really good at doing Diels-Alder. So here is an example of a bad diene. And in fact, this diene cannot actually be used as a diene in Diels-Alder reactions. And the reason why is that the diene that we're looking at here is locked in an S-trans conformation. So if we just compare that to the S-trans above, we see that this diene cannot actually rotate into an S-cis conformation, and so therefore it cannot be in that structural requirement for a Diels-Alder reaction to occur. On the other hand, here is a diene that will rapidly undergo Diels-Alder reactions. In fact, you don't really need much in your flask to have this diene engage in Diels-Alder reactions. And we can kind of now see why. And the reason here is because this diene, unlike the one on the left, is actually locked in an S-cis conformation, which means that it's really not going to change out of the required conformation for Diels-Alder, making it very susceptible for Diels-Alder reactions. Okay, so now in the last part of this video, we're going to focus on the stereochemical outcomes of Diels-Alder reactions. And we're going to actually classify stereochemical outcomes on the three scenarios of Diels-Alder reactions. In the first scenario, we're going to focus on acyclic dienes, so dienes that are not in a ring, with monosubstituted dienophiles. So here are two reactant examples, and we see that our dienophile has one substituent on it, which is an electron withdrawing group, which we've already asserted that makes a good dienophile. And here is a curved arrow mechanism for this reaction, once again. And so our product will actually end up looking like this. And notice we have two stereoisomers of our product, one where that aldehyde functional group is sticking out towards us, so it's wedged, and the other where the aldehyde functional group is going away from us. And both of these enantiomers are formed at equal concentrations. So we have a racemic mixture of both of the enantiomers in our flask. So the question is, why are we forming both of these stereoisomers or enantiomers at equal concentrations? And to understand this, it all has to do with what is going on at the transition state of this reaction. And I'm going to draw the transition state leading to both of these products now. Okay, so we see in here that the transition state really all has to do with the electrons forming a closed loop between the diene, the four atoms of the diene, and the two atoms of the dienophile. And so at this stage, your aldehyde can equally be wedged or dashed, and there's really no reason why one of those two spatial positions should be favored in this particular state. And so because of that, we see that both are equally likely, and therefore you should expect both stereoisomers of the product to be formed. Okay, so under these conditions of an acyclic diene with a monosubstituted dienophile, you tend to get a non-stereoselective reaction where all stereoisomers that can be formed are formed. Okay, so in the second scenario, we will focus on Diels-Alder reactions that involve dienes reacting with disubstituted dienophiles. And I'll use two examples to showcase the stereochemical outcomes in this scenario. In example one, we see that we're using a cis dienophile to react with our diene. And so our product that we observe is a cis disubstituted cyclohexene. So what we see here is that essentially the stereochemistry of a dienophile transfers into the stereochemistry of the product, right? So a cis dienophile forms a cis disubstituted cyclohexene. Please note here that because we formed a meso compound, that we only see one possible product here. Here's example 2. In example 2, we take the same diene, but this time we react with a trans Dienophile, and we see that in our product, we form two stereoisomers of our product, both of which are trans disubstituted cyclohexenes. And so once again, the stereochemistry of our reactant dienophile transfers over to the stereochemistry of the product of the Diels-Alder reaction. And so what this tells us is that for the scenario when we're using disubstituted dienophiles, our Diels-Alder reaction is stereospecific. And all that means is that the stereochemistry of our reactant dictates the stereochemistry of our product. Okay? And so you can almost track it. Cis goes with cis and trans goes with trans in our stereochemical outcomes with di-substituted dienophiles. So in our last scenario, we focus on cyclic dienes with substituted dienophiles. So here's an example of a cyclic diene on our left, and here's an example of a substituted dienophile. So let's once again trace out what the mechanism will look like here. So here's the curved arrow mechanism. I've also numbered my dienes, so with the 1, 2, 3, and 4, and my dienophile 1' and 2'. Also, please take note of the starred carbon, which is not numbered. It's not part of our diene that's going to be bonding, but it is also part of the molecule, so we have to draw it in our product. Okay, and here are the major products of this reaction. Because that starred carbon is within the ring of the diene, we end up forming this bicyclic ring. So we see there's a bridge where that star is on both of these major products of the reaction. So that's the big difference, is that you have this additional bridge on this particular ring. Okay, so with that in mind, that's the major product because of the stereochemical outcomes. So we look at what is going on here. Notice that the aldehyde substituent or your dienophile substituent ends up on the same side as the forming product pi bond. So that pi bond that ends up forming between carbons 2 and 3, as opposed to the bridge between carbons 1 and 4. And so the question is sort of why? Why is that the major product of this reaction? But to do that, let's just go ahead and contrast this to what the minor products would look like. And here are the minor products. So in the minor product, the dienophile substituent ends up on the opposite side of the product pi bond. So let's just go ahead and define these two stereochemical relationships so that we can then use it to understand why we actually get this stereochemical preference. When the dienophile ends up on the same side as the product pi bond, we call this the endo product. And then when the dienophile ends up on the opposite side of the product pi bond, we call it the exo product. Okay? And so for Diels-Alder reactions with cyclic dienes and substituted dienophiles, the endo product is favored over the exo product. Okay, so as a recap, we have our cyclic diene, we have our substituted dienophile here, and we see our endo product as our major product. So the reason why this is the case has to deal with the transition states leading to these two products in the reaction. And so what I have drawn here are the transition states leading to these two endo major products in the reaction. And so what I want to just focus on is the position of the substituent on the dienophile and where it is with respect to the location where you're going to have the forming pi bond in this particular product. And what I've tried to do here is I'm using sort of a green crayon to show you that there is actually a contact between that pi bond area of the diene and the pi system of your dienophile substituents. And what you really should know here is that when that substituent is positioned closer to that pi system of the diene, well, what happens is that there is actually a favorable interaction between the diene pi system and the electron withdrawing group on your dienophile substituent. And that favorable interaction then helps to control the stereochemical outcome towards forming the endo product. So please notice that here, the substituent is positioned towards the diene pi system and away from the bridge, right? So the bridge is on the opposite side of the of the dienophile. Okay, and so whenever you need to predict the major product and stereochemical outcomes for Diels-Alder reactions between cyclic dienes and their substituted dienophiles, you really want to be careful about ensuring that you are depicting the endo product in this reaction and not the exo product in this reaction for the major product of this reaction. Okay, so to recap, we have situated Diels-Alder reactions as an example of a cycloaddition reaction, which is categorized under pericyclic reactions. We have drawn the mechanism of Diels-Alder reactions, identified what a good diene and a good dienophile is, and why you need both in order to make an ideal Diels-Alder reaction. And we've also then looked at three scenarios of stereochemical outcomes for Diels-Alder reactions. Okay, thank you so much for watching this video, and I will see you in class.